You have been convinced that the mines of the 19th century were merely a business for extracting metal. However, this version cannot withstand any critical scrutiny when comparing dates, technologies, and biological facts. Why were people made to work in temperatures that melted candles when it was economically impractical? Why were closed ecosystems created and experiments conducted on the physics of Earth in industrial facilities? Who needed data on the limits of human endurance in extreme conditions long before the space age? Official reports attribute everything to the greed of owners. But greed doesn't spend fortunes on projects that will only pay off in a century. And the main question is, what were they really searching for or hiding at depths that even scientists were afraid to descend to? Imagine complete darkness. Not the kind of darkness found in a room with closed curtains. It's something else. The kind where the light of a candle exists for exactly 30 centimeters, and beyond that, a wall of gloom. Beneath your feet is a wooden platform the width of a dining table. It moves. Up, down, evenly, methodically, like the pendulum of a giant clock. Above your head is not the ceiling of a mine. Above your head is the bottom of the Atlantic Ocean. You know this because you can hear it. The muffled roar of water, the movement of stones, the distant sound of waves crashing against rocks 100 meters above you. And you are 600 meters below those rocks. The smell here is unique. Hot metal, wet granite, the sweat of dozens of people working at neighboring levels. The air is thick. It's pushed down from above through a system of wooden ducts, but at this depth, it loses its freshness long before it reaches you. You breathe in what's left behind by everyone above you. In this air is the scent of every person who has worked in this shaft over the past few hours. Now you need to jump. Another platform is moving in the opposite direction. Yours is going down. That one is going up. At the moment they align in height, you have 1 second. 1 second to step over. Not to jump, but to step over, carefully, without any excessive movements. Because if you miss, there is no safety net. There is only the shaft, and 200 meters to the next horizon. You did it in the morning. You will do it again in the evening. Tomorrow, again. And the day after tomorrow. Throughout your entire working life. As long as your body holds up. As long as your hands cling to the rungs. As long as your foot doesn't slip on the wet wood. People who worked in the Levant became very skilled at one specific ability: jumping accurately, in the dark, to a designated spot 600 times in a shift. Those who did not become good at it did not last long. This is not a fantasy. This is a workday in the Levant mine, Cornwall, in the mid-19th century. This is how they descended and ascended every day. This is how the man-engine system operated. A mechanical lift that was not a lift at all, but a series of moving wooden steps designed for a person to jump across. On October 20th, 1919, the wooden beam that powered the entire structure broke during the descent. 31 people did not return home. After that, the mine was closed. But the steam engine from 1840 still stands in its place. And the tunnels under the ocean do too. I will tell you about 7 mines from the 19th century. 7 places where depth ceased to be merely a production task and became something else. They are all documented. They all exist. And each has an official version. It's just that when you start to count timelines, capacities, volumes, temperatures, the official version begins to crack. Not because someone has hidden something, but because the right questions were never asked. This is not conspiracy theory. This is engineering and mathematics. But before we start counting, ask yourself one question. When was the last time you thought about what lies beneath your feet? Not in a philosophical sense, literally. How deep does the earth go under the city you live in? What's there, 100 meters down? 500? A kilometer? Most people never think about it. We live on the surface and perceive it as an absolute reference point. Everything important happens above. History is made up there. Wars, trade, politics, art, all of this takes place under the sky. But in the 19th century, a group of people made a different decision. They descended downwards. Not 100 meters, nor 200. A kilometer and a half. 3. In conditions that official science deemed impossible for human work. With technologies barely adequate for the task. With resources that were not designed for such a scale. Why? This question is rarely asked. Because the answer, metal extraction, seems obvious. Metal is necessary for industry. Industry is needed for progress. Everything is logical. Everything is clear. Let's move on. But once you start counting, the logic falls apart. The costs are too high. Technologies are too ahead of their time. Decisions are made against economic rationality. Again and again, in different places, in different countries, with different people, the same picture. Someone was spending impossible resources on an unattainable depth. And someone chose to continue, even when everything said, stop. Let's start with the quietest. July 1875. Przybram, Bohemia, Austro-Hungarian Empire. The mountain engineering team records the mark. 1,000 meters. Exactly 1,000. The St. Adalbert mine has reached a depth that no mine in the world has achieved before it. Vertically, through granite, all the way down. To understand what this means, imagine you are standing at the top of the Eiffel Tower. Look down. Below you is 300 meters. Now multiply that distance by a bit more than 3. That's where the mine was. Underground. In the dark. At a temperature of 30 degrees. With a rope being the only way up. In a few months, the Austro-Hungarian Empire will issue a silver florin, a coin, featuring an image of a mine shaft and the date. The only coin in history released in honor of reaching depth in a mine. Not a victory in war, not the annexation of territory, not the birth of an heir. A hole in the ground a kilometer deep. Here's the first question. Why? The most obvious explanation, a symbol of progress. The empire took pride in its industry. The florin, propaganda, a tribute to the era. It sounds logical, until you look at the numbers. The Przybram mining district accounted for 97.7% of the total silver and lead extraction of the Habsburg monarchy. Not a part, not a significant share. 97%. This mine was not merely a production site, it was the financial foundation of an entire empire. The silver that lay here supported the value of the Austrian currency, financed the army, and provided loans. Remove this single mining district, and the financial architecture of the state collapses. That is precisely why the coin. The florin was minted in honor of the record, not because they wanted to immortalize an engineering achievement. It was minted because the achievement was political. 1,000 meters down meant another 100 years of silver. And 100 years of silver meant 100 years of the empire's creditworthiness in international markets. The coin was a signal to creditors. The foundation will hold. And this foundation was suspended on a steel cable 1 kilometer long. Consider this task. Wire rope was invented specifically for the needs of the mining industry in 1834 in Germany because hemp ropes could not withstand the loads. But even a steel rope a kilometer long represents a different scale. It has its own weight. At a length of 1,000 meters, its own weight at the upper attachment point creates a load comparable to the weight of several loaded carts. Add to this the weight of the cage itself, the weight of the miners, the weight of the lifted rock, and include the dynamic shock at the moment of the lift start, when the system jerks into motion. How can we calculate that the rope will hold? Without computer modeling, without metallographic analysis, without data on the metal's accumulated fatigue. They did it in Prashibhrama. The Breitfeld-Deneck steam engine from 1889, which powered the lift, weighed hundreds of tons. Calculations were done on paper, with a pen, using logarithm tables. And they were not mistaken. The mine was operational. But there is another layer to this story. In 1849, even before the record was set, a mining academy was established at the mine. It was not a local educational institution, but an international one. Engineers from Britain, Russia, Prussia, and the United States of America came here. Prashibram developed global standards for deep drilling, surveying, and load calculations for lifting systems. From here, the methodologies spread throughout the industrial world. Look at the ventilation. At a depth of 1,000 meters, the rock temperature exceeded 30 degrees. Without forced air movement, people could not work there. There were no electric fan systems. The solution? A system of interconnected vertical shafts, where hot air escapes through one, while fresh air enters through the other, due to differences in temperature and atmospheric pressure. This scheme was calculated mathematically. It worked. It began to be copied around the world. The cost of this knowledge became evident in 1892. A fire at the neighboring Marion mine, a part of the same complex, claimed the lives of 319 people. 319 lives in a single day. The worst mining disaster in the history of the Austro-Hungarian Empire. The cause was an accumulation of mine gas ignited by an open flame from a candle. And here's what is characteristic. Mine gas at such depths is a well-known problem. The engineers of Chibram were aware of it. The ventilation system was designed, among other things, to remove it. But the calculations were made for normal operating conditions. When the conditions were disrupted, one random fire in the wrong place, the entire system turned into a trap. The work was not stopped. The coin had already been minted. The academy continued its work. The mine kept extracting. Because the price had been agreed upon in advance, not by people, by the system. This is the first thing that unites all 7 entities. Depth always cost more than what is recorded in the official balances. And now, a question that scientists raised several years later. In 1894, an unusual experiment was conducted at the Tamarack mine in Michigan. 2 freely hanging plumb lines were lowered to a depth of about 1,000 meters. According to Newton's laws of physics, they should have hung perfectly parallel. After all, both indicate the direction to the center of the Earth. But the plumb lines diverged. At a depth of 1 kilometer, they were further apart at the bottom than they were at the top. Much further than they were supposed to be. This became one of the first direct measurements confirming that the Earth is not a perfect sphere, but a slightly flattened ellipsoid. The physical law, which had previously been a theory, received direct measurement deep within the mine. Shibrum did not conduct such an experiment. However, he created the very possibility, the engineering standard of a kilometer-long shaft, without which such measurements would have been impossible. Scientific knowledge about the shape of the Earth became available because mining engineers learned to keep a cable at a kilometer depth. But there is a detail about the rope that is usually overlooked. The steel wire solved the problem of rotting hemp, but it created a new one. Every start of the ascent creates a jerk, a dynamic force that exceeds the static load by several times. With incorrect calculations, it is precisely this jerk that can tear the rope. Not gradual wear, a single impact at the moment of the start. The engineers of Pribram took a safety factor of 8. The cable was designed to withstand a load 8 times greater than the standard. It was expensive, heavy, and required more powerful machinery. But the cable never broke. Not once during the entire operation of the mine. This happened at a time when such accidents were common at other sites. This is engineering philosophy, not luck. It's not about doing enough, but doing with a margin so that even the worst-case scenario won't collapse the system. This philosophy spread from Pribram through the mining academy across the industrial world. Now let's move to the other side of the world. Michigan, United States of America, 1897. The Calumet and Hecla Mining Company built the Red Jacket shaft from 1889 to 1897. 8 years of construction. The final depth is 4,900 feet, almost 1,500 meters straight down. For comparison, this is roughly like stacking 4 Eiffel Towers on top of each other and going even lower. The lifting machines from Whiting had a power of 8,000 horsepower. 8,000. To grasp the scale, a battleship of that era developed between 8 and 10,000 horsepower. The company invested in one lifting mechanism, the power of a warship. Stop on this detail. A battleship is a machine of war. It is built by states. This weapon requires an industrial base, special steel, precise mechanics, and professional crews. A private mining company in the American state of Michigan has established the same power in a mine shaft. Without a military order, without government funding, simply because it deemed it necessary. And here's a question that textbooks don't ask. The Red Jacket shaft was built outside the ore body. In the early years of operation, not a pound of copper was extracted from it. The official explanation? A safety shaft, in case of a fire in the main drifts. If the main entrances to the mine are blocked by fire, the Red Jacket will provide access to the lower levels. Okay, let's assume that's the case. Then answer one question. Why does the insured object need a pump with a capacity of 51 million gallons of water per day? 51 million gallons. That's approximately 200 million liters a day. Such a volume is enough to supply water to a large American city. The insurance pipeline, which no one intended to use in normal operation, is equipped with a pumping system for a megacity. This is not insurance. It is a different concept. Infrastructure redundancy is an idea we know from nuclear power plants, military command bunkers, and communication nodes in case of nuclear war. When the main system must have a completely independent backup, capable of taking on the full load at any moment. In the 19th century mining industry, such an approach was not applied anywhere. Nowhere except Red Jacket. Let's approach it from another angle. Calumet and Hecla produced more than half of all the copper in the United States at certain times. Copper at the end of the 19th century was not just a metal. It was wires. It was the telegraph. It was the telephone. It was electrical networks. Thomas Edison built his first electrical systems using copper from Michigan. Whoever controlled this copper controlled the pace of electrification across the entire continent. When you understand the scale, the logic of insurance starts to look different. If the main lines falter, the electrification of America slows down. Telegraph lines degrade. Telephone networks do not expand. This is no longer just a mine fire. It is a blow to the country's infrastructure. And now, add another fact. The total depth of the system, taking into account the inclined subshafts, was nearly 3 kilometers, 9,600 feet, in the 19th century, with steam engines, without electricity, without modern alloys, without computer load calculations. At a depth of 4,900 feet, the temperature of the rock was 86 degrees Fahrenheit, about 30 degrees Celsius, plus the humidity from the mine water, plus the heat from the operating machines and the bodies of hundreds of people. The workers were in conditions that modern occupational medicine would classify as extreme. And the last thing to say about Calumet and Hecla is that a town grew around the mine. The town of Calumet became one of the richest per capita places in the United States. An Italian theater with luxurious acoustics, a Carnegie Library, a hospital, parks, electric lighting, earlier than in most cities in the country. All of this was funded by a copper vein that extended 3 kilometers down. In 1913, a tragedy occurred in this theater during a Christmas party for the miners' children. Someone shouted, "Fire!" The crowd rushed to the exit, crushing 73 people. Most of them were children. There was no fire, just panic, just a stampede. Killer irony, the most advanced technologies of the 19th century, concentrated underground, could not protect children on the surface from human panic. 3 kilometers underground, perfect engineering. On the surface, human chaos. But there is yet another layer to the story of Red Jacket that is rarely discussed. Copper from Michigan was special, not in a metaphorical sense, but in a literal chemical sense. The copper of Calumet had exceptional purity, 99% or more. This is not standard ore copper that needs to be refined through complex processes. It is virtually pure metal, extracted from the earth in nuggets. Such purity is critical for electrical conductors. Impurities sharply reduce conductivity. A telegraph line made from impure copper loses signal sooner. An electrical grid using poor quality copper wastes energy as heat. The entire first wave of electrification in the United States, from Edison's first lines in New York to the transcontinental telegraph, was built on this very metal. It's a monopoly not on volume, but on quality. Now look at the timeline. The Red Jacket shaft began construction in 1889, right at the moment when copper ceased to be just an industrial metal and became an infrastructural resource essential for the communication speed across the entire continent. Red Jacket was not built for immediate extraction. It was built to ensure that extraction would never cease. Someone made this decision long before electricity became commonplace in most American cities. And here it is worth noting a fact that typically goes unnoticed. Concurrently with Red Jacket, on the other side of the country, in Nevada, another person was digging a completely different tunnel. The Sutro Tunnel. 6 kilometers through rock to drain water from the Comstock silver mines. The goal was to break the banking monopoly that controlled access to the ore. 2 engineering solutions in 1 decade. One was built to protect the copper monopoly, the other to dismantle the silver monopoly. Both worked through water. Both worked through depth. Now to Britain. Sunderland, 1826. The Pemberton family begins drilling. They chose a spot on the banks of the Ure River. The geologists of that time, by then geology had already become a serious science, unanimously declared, "There is no coal here." Beneath the layer of magnesium limestone, there cannot be coal seams. This is a geological law confirmed in dozens of other locations. Digging there is like searching for water in granite. They were digging for pumpertorns. The first year, the second, they passed through aquifers that drowned any progress. Every subsequent meter required pumping out huge volumes of water. The money was running out. There were no deposits. Experts kept repeating, "Coal is impossible here." The Pembertons continued. 8 years. 8 years of drilling in a place where, according to all scientific knowledge, there was no coal. In 1835, at a depth of 481 meters, they found coal, a record depth for coal mines at that time. And the location where it was discovered contradicted all existing geological models. The question isn't about what they found. The question is, what compelled them to dig where science said no? On what basis were they confident enough to invest a fortune and 8 years of their lives? Historians refer to this as entrepreneurial intuition, luck, or perseverance. But there's one thing that doesn't fit. The magnesian limestone in this area is a layer nearly 200 meters thick. To dig through it for 8 consecutive years, one must not just believe in coal. One must be certain that it exists. Such certainty does not come from nowhere. It is either based on data or on knowledge that official geology has yet to possess. Where did it come from? The official history is silent. But there is something that historians usually overlook. By the 1820s, there existed an entire network of informal mining knowledge in Britain. Coal miners working in the mines of Durham and Yorkshire passed down observations from generation to generation that never made it into any scientific treatises. They knew where water flowed underground. They could read the outcrops of rock on the surface, the nature of the cracks, the angle of the strata, the behavior of groundwater. Academic geology in the 1820s was still young. The practical knowledge of those who had been digging for decades was not. It is likely that the Pemberton family knew something from this informal source. Perhaps it was an old document. Perhaps it was the account of a miner who had seen a certain type of rock in the right place. This knowledge did not withstand scrutiny from academic geologists, as it never even reached them. It lived in the minds of the people who worked with their hands. And then a paradox arises. Official science said no because it did not have the correct data. The data were with those whom science did not ask. The Pembertons found themselves in the right place between these two worlds. Look at the result. The Monk Wearmouth Colliery opened right by the River Wear. Here they built a system of staiths, gigantic wooden platforms from which coal would fall directly into the holds of ships. There was no manual loading. There were no barrows to move it. The coal moved under its own weight down sloping chutes, gaining speed, and cascaded into the hold. Loading the vessel took hours instead of days. The throughput is thousands of tons per day. This is the prototype of automated coal terminals, built from brick and oak 50 years before their official invention. It fueled the British fleet. The British Navy in the 19th century transitioned from sails to steam. Coal became a strategic resource, just as oil would become in the 20th century. The fleet did not move without coal. An empire could not exist without a fleet. The Monk-Wearmouth mine provided a direct link between the Earth's depths and the naval power of the nation. Now, a small detail that is usually overlooked. In the year 1902, there were 2,135 people working in the mine. That's a whole small town descending underground every day. The logistics of a workday for such a number of people is a task of army scale. Shifts, nutrition, lighting, ventilation, lifts, water drainage, tools, and rock transport. All of this functioned continuously in one point under the river at a record depth. In 1868, Monk-Wearmouth installed the last vertical single-cylinder steam engine of its kind in the world. The last one. Not the first, the last. Everything else had already transitioned to more modern designs. Monk-Wearmouth clung to the old because the old worked, and because changing a functioning system meant risking the cessation of coal supply to the fleet. The mine closed in 2003. In its place now stands the Stadium of Light, the home arena of Sunderland. Under the stands, where the shafts used to go down, where 2,000 people worked, where coal once fell into the holds of ships, there is now the roar of the crowd and the light of floodlights. The pit wheel has been preserved as a monument at the entrance, and the old brick wharves along the banks of the Weir River, they are still there too. 3 mines, 3 sites, and 3 unanswered questions. A coin instead of an explanation. A pump for the metropolis in an insured site. Coal where it shouldn't be. The next 3 sites, a different order. There, the questions are not posed by the economy. There, the questions are posed by the physics of the human body. Brazil, state of Minas Gerais. Morro Velho Mine, operated by the British company St. John del Rey Mining Company since 1834. Gold. By the end of the 19th century, the mine extended to a depth of nearly 1,800 meters. A cascade of vertical and inclined shafts followed the ore vein at a 45-degree angle. The temperature of the rock at the working depth is 55 degrees Celsius. Not the air, the rock. Imagine, the walls are burning. Not literally, they're just hot. Touching the granite feels like touching a scorching frying pan. The air is saturated with moisture because, at this temperature, water evaporates from all surfaces. The effective perceived temperature is above 60. The human body starts to lose control at 42. At 60, it's no longer a working environment. It's a survival environment. The candles were melting. This is not a metaphorical expression. A regular stearin candle deforms at temperatures above 50 degrees. The wax cap melts away before the wick has a chance to provide the necessary light. Engineers at Morro Velho developed special holders that allowed the candle to burn vertically even in a semi-melted state. It may seem like a trivial detail, but it signifies a great deal. Every element of work at such depths required rethinking. What worked on the surface broke or ceased to function here. Until 1879, slaves worked in the mine. A British company, a British Victorian progressive company that officially prohibited slavery in the metropolis since 1833, and yet legally owned people in Brazil for another 46 years after that ban. Because Brazil was not British territory, the company operated under Brazilian laws, and the thousands of kilometers separating principle from practice served as the perfect shield against uncomfortable questions. Morro Velho is not an exception to Victorian values. It is their exact reflection. Progress exists on the surface. The real cost lies beneath, in the darkness, in 50-degree heat where no one sees it. Now add logistics to this. Until the end of the 19th century, all the energy for the mines was supplied by water. Not steam, water. Huge aqueducts brought water from the mountains. Water wheels raised the ore, powered crushers, and pumped groundwater from the lower levels. To extract gold from Brazil, the British built a water supply system that was used in Europe to supply cities. All of this was for the metal located 2 kilometers underground. The total length of the aqueducts was hundreds of kilometers. It was the infrastructure of an entire Brazilian state, built so that the wheels turned at one specific depth. In 1867, a catastrophic collapse occurred. The work was halted. Then it was restored. In 1886, there was another collapse. Once again, it was restored. By the 90s, the gold content in the ore at that depth was declining. The cost of maintaining operational efficiency at a depth of 1.5 kilometers was increasing every year. The economy was saying, "Close it down." They didn't close it. In 1920, the first industrial air cooling system in mining history was established at Morro Velho. Mechanical cooling, pipelines, distribution across different levels. The mine transformed into an autonomous ecosystem with a controlled climate. This is a concept we know from submarines and orbital stations, in the Brazilian jungle, in a gold mine. British engineers working with this system developed physiological norms for human performance in extreme heat conditions. When exactly performance begins to decline? How much fluid is needed to restore functions? How long a person can remain at different temperature levels without irreversible consequences? This data was meticulously documented. In the 20th century, they were needed once again. During the design of the first atomic reactors, where workers faced similar thermal conditions. The knowledge gained in the Brazilian mine at the cost of human lives became the foundation for the standards of the nuclear industry. This is not a coincidence. This is a system. The depth created conditions in which one could study what cannot be explored on the surface, and someone understood that this data would be needed later. Let's return to Britain, Cornwall. The Dolcoath Mine, the Queen of Cornwall. Its depth is 1,006 meters, the deepest tin mine in the region. By 1895, the journey of a miner from the surface to the working face took 3 hours one way. 3 hours down, 3 hours up. A work shift in between. A person spent half their time just moving between 2 worlds, the surface and the depths. Calculated. A 6-hour workday plus 6 hours of travel, totaling 12 hours, every day, 6 days a week. And this is despite the fact that by 1882, Dolcoath had 12 miles of active tunnels and another 40 miles that were abandoned. 40 miles of drifts that nobody traversed because the rock had been worked out or the conditions became impossible. An underground city with inhabited quarters and the dead. At Dolcoath, Richard Trevithick worked, the very one known as the father of the locomotive. Here, he tested steam pump machines with cylinders measuring 85 inches in diameter. That's over 2 meters across. The cylinders generated steam pressure that was unimaginable by the safety standards of that time. Boilers would explode even at half the working pressure. If such a cylinder burst, and they did burst, it unleashed a wave of scalding steam in a confined space. Why here specifically? Why not on the surface? Not in a factory? Not in a safe laboratory? Because the mine funded experiments. The tin extracted financed the trials. Dolkoth was a laboratory maintained by production. Trevithick received the conditions, the mine received pumps. When the tests were successful, the technology was implemented in railway locomotives. The mine provided the foundation for the next industrial revolution. Stop and reflect on this mechanism. The railway radically transformed the 19th century. It made industrial civilization in its current form possible. The speed of transporting people and goods increased several-fold. New markets, new cities, and a new economic logic emerged. All of this became possible because someone in a Cornish mine learned how to build high-pressure boilers without them exploding. But Trevithick received not a penny from the railway revolution he spawned. He passed away in 1833 in poverty, when locomotives were already being built by the thousands, and Stephenson had become famous and wealthy from technologies rooted in the trials of the Delaval. The one who takes the real risk in the mine is not the one who receives dividends in London. And then something happened that can't be explained by economics or technology. Among the workers at Dolkoth, cases of severe anemia began to emerge. Chronic fatigue, pallor, and increasing weakness. People were written off as suffering from the rigors of hard labor, until the doctors took blood samples and discovered a parasite. Ancylostoma duodenale, the hookworm, an intestinal parasite. The organism requires a constant temperature of at least 20 degrees, high humidity, and moist soil for survival and reproduction. Cornwall is in the north of Britain. The Atlantic wind, frequent rains, and an average annual temperature of around 11 degrees. A crooked head cannot survive there. It should not. But deep within Dolkoth, it thrived. It found the perfect environment, a constant temperature of around 25 degrees, 100% humidity, damp soil on the floors of the shafts. It multiplied. It moved from person to person through contact with the infected rock. It established a sustainable biological cycle deep within a British mine, one that would be impossible under normal conditions in Cornwall. This means one thing. The mine has created within itself a climate that does not exist and cannot exist at this geographical point. A stable, reproducible environment, warm enough and humid enough for the survival of tropical organisms. A kilometer deep in the granite of Cornwall. The discovery shocked the medical community in Britain. Previously, the disease was considered a tropical illness, imported and exotic. It turned out that all it takes is to create the right conditions for it to thrive anywhere. The parasite was noticed because it was killing people. Everything else that survived in this artificial tropical climate a kilometer deep remained unrecorded. Medical data collected at Dolkoth regarding the physiology of workers under high temperature and humidity conditions were later used in developing labor standards at the early nuclear facilities, where engineers faced similar thermal stresses. The knowledge born from the miners' ailments became the foundation for regulations in the nuclear industry of the 20th century. This, too, is absent from any official records. In 1893, a collapse occurred at a depth of 800 meters. Workers were buried under a layer of stone. Work was resumed once again, because Dulcoth had no reason to stop while tin was still valuable. Dulcoth closed in 1921, not due to accidents, but because of the falling tin prices. The metal ceased to be worth the cost of its extraction. That alone put an end to the mine. Not disasters, not parasites, not the 3-hour journey to the face in one direction. Now, Poland, Tarnowski Mountains, Silesia. Look at the numbers: 20,000 mine shafts, 150 kilometers of horizontal galleries. This is not just one mine. This is an underground city. A network that was built from 1784 to 1880, nearly 100 years of continuous underground construction. Consider the scale. 150 kilometers is the distance from the center of Warsaw to the Polish coast. It's the length of the country in one direction. All of this has been dug by hand under Silesian soil, using explosives for blasting, drained and maintained in working order. Every meter of those 150 kilometers represents the labor of a person with a shovel. The main problem of this deposit is water. The influx of underground water was 3 times higher than the average European rate for comparable deposits. Every meter of excavation was immediately filled with water. The mine was sinking faster than it could be constructed. In the year 1787, the Prussian king made a decision. He personally organized the delivery of a Watt steam engine from Wales. He didn't buy it. He arranged for its transport across half of Europe. The disassembled machine was transported by sea and then on roads. The delivery took months and cost a fortune. It was the first steam engine in continental Europe. Not for the Navy, not for a factory in the capital, but for a mine in Polish Silesia. Why here specifically? Why was the Prussian monarch spending state resources on draining water in one mining area? Official response: silver and lead for Prussia. Strategic metal. The logic is clear. But water levels 3 times above the norm. This is not just a geological feature. This is an anomaly. There is a question that geologists rarely ask. Where does such a volume of water come from? The standard aquifer in limestone is predictable. Its reserves are finite, the inflow is stable, and it decreases as extraction continues. In the Tarnowski Mountains, the inflow has not decreased. For decades. There was as much water in the 100th year of extraction as in the first, as if the source had not dried up. There is a theory. The excavators uncovered an ancient, isolated reservoir. Not a standard aquifer, but a volume accumulated and sealed in limestone for millennia. When it was breached, it began to slowly drain through all the existing cracks, continuously feeding the system. This explains both the anomalous volume and the stability of the inflow, as well as why the water behaved differently in this specific location than anywhere else. If that's the case, the Prussian king understood this earlier than the geologist did. Or he was informed. Because the reaction was proportional to the threat. The first steam engine on the continent. Now, about how exactly this decision was made. The Prussian king Friedrich Wilhelm II in 1787 did not simply order a machine. He sent a delegation to Cornwall, specifically to study Watt's machines in action, understand their design, and ensure they would be suitable for the conditions of the Tarnowski Mountains. The delegation spent several weeks in Britain. Upon their return, they prepared a technical report with calculations. Only after that did the order come. This is not an impulsive decision by a wealthy monarch. It is a systematic assessment of the technology, its applicability to a specific task, and the willingness to pay for its implementation. In 1787, such an approach to technological borrowing was rare. Most states copied technologies spontaneously, through industrial espionage or by hiring random craftsmen. Prussia conducted an official engineering assessment. The result was not only a functioning machine. The result was an understanding of how steam technology works from the inside. The Prussian engineers who observed the installation and launching of the machine gained knowledge that later spread across continental Europe. The Tarnowski Mountains became the entry point of the Industrial Revolution on the continent. But here's what happened next. The engineers who designed the drainage tunnels, primarily the tunnel for the black trout, built them not just to divert water. They calculated the slope and direction so that water would not just leave the mine, but rather be channeled into the municipal water supply of Silesia. The outlet point of the tunnel is higher than most wells in the surrounding towns. The drainage flow operates under its own pressure, without pumps, solely by the law of gravity. Industrial waste has become the drinking water infrastructure of the region. This is the first historical example where what hindered metal extraction has turned into a resource for the lives of thousands of people. It was designed intentionally by someone who thought not only about the mine, but also about the region surrounding it. Pay attention to the scale of this thinking. Mining engineers in the Tarnowski Mountains were solving urban water supply problems, not as a primary objective, but rather as a side effect of mine planning. This is not charity. It represents a different understanding of the task. The mine is viewed not as an isolated extraction site, but as part of a territorial life support system. Such systemic thinking would only emerge in state planning in the 20th century. Today, the Tarnowski Mountains are a UNESCO World Heritage Site and the only underground boat route in the world through a 19th century drainage tunnel. Tourists sail in the same places where miners pumped out water that was later consumed by entire cities. 35 kilometers of the tunnels are open to visitors, while the remaining 115 are not. Water, which was once a problem, has become a resource. No other entity on this list has turned its greatest threat into its main product. But there is another object that is almost never included in this list. It usually remains in the background because its story appears not as an engineering puzzle, but as a financial blueprint, which makes it all the more intriguing. Spain, province of Ciudad Real, Almaden Mine. In operation since the 3rd century BC. 2,000 years. This is the oldest and largest mercury mine in the world. During this entire time, 250,000 metric tons of mercury have been extracted here, exactly 1/3 of the total amount that humanity has ever mined from the Earth. Mercury, a liquid metal, the only metal that exists in a liquid state at room temperature. Heavy, mobile, shiny, like a small living mirror. And every gram of it is a poison that insidiously penetrates through the skin and lungs. Question: why was it needed in such quantities? In the year 1550, the Spanish metallurgist Bartolomé de Medina made the following discovery. If silver ore is mixed with mercury, the mercury absorbs the silver, forming an amalgam. Then the amalgam is heated. Mercury evaporates, leaving silver behind. Purely, cheaply, without complex smelting furnaces. This method was called the patio process, and it allowed for the extraction of ores with low silver content, which were previously considered unprofitable. Consider what this meant. Without mercury, there was no cheap silver from America. Without cheap silver, there was no financial base for the Spanish Empire. All the silver mines in Mexico, Peru, and Bolivia depended on a continuous supply of one ingredient. That ingredient was mercury from Almadane. Almadane was not a mine. It was a valve that regulated the flow of wealth from an entire continent. This is why the mine was not managed by ordinary miners. In 1525, Charles V, Holy Roman Emperor, transferred the rights to manage the mine to the Fugger family, German bankers from Augsburg, in exchange for loans to the Spanish crown. The entire silver chain of the New World, the whole financial machine of Spanish colonialism, functioned because a Bavarian banking house supplied mercury. It lasted for more than 100 years. In 1835, during the height of the First Carlist War, the mine came under the control of the bank N.M. Rothschild and Sons. At the same time, the Austrian branch of the same family acquired the second-largest mercury mine in the world, Idrija in Slovenia. The result? 2 mines, 1 owner, the entire global mercury market, in one set of hands. A complete monopoly. Whoever controlled mercury controlled the pace of silver extraction in Latin America, and thus the rate of filling global reserves. This, in turn, influenced the conditions of lending across 3 continents. The liquid metal from the Spanish mine was a lever of the world financial system. Now, about the price of this lever. Mercury evaporates at any temperature. The vapors are invisible. They are odorless. They penetrate through the skin and through the lungs. As early as the 16th century, the physician Gabriele Falloppio noted that miners in mercury mines did not live longer than 3 years after starting work. 3 years until paralysis, until tremors, until the loss of reason. In 1566, the Fugger family could not find enough volunteers and requested the Spanish king to send prisoners. The first batch consisted of 30 people from the Toledo prison. By 1583, this number had risen to 40. Documents record a daily ration of meat, bread, and wine, annual issue of clothing, and an infirmary. Officially, everything was in order. 24% of the prisoners died before their term ended. Most of them died from mercury poisoning. Nearly all of the survivors suffered from tremors, memory loss, and an increasing inability to move steadily. Chronic mercury poisoning is the oldest documented occupational disease in history. It was here that it was first clinically described. Hand tremors that spread to the body, night terrors, irritability, dementia. The medical term is erethism. Miners referred to it more simply as mine sickness. Have you heard the story of the Mad Hatter? It's not a fabrication. Hatters of the 18th and 19th centuries used mercury compounds in processing felt. They truly went insane. Lewis Carroll incorporated this imagery in Alice's Adventures in Wonderland. However, the syndrome itself was described 2 centuries before hat production, specifically in Almaden, among the miners who extracted mercury for the silver economy of the Spanish colonies. Everyone knew about the disease. No one stopped. Because mercury was needed. Because without it, silver mining in Mexico would slow down. Because creditors, first in Augsburg, then in London, kept an eye on the speed of extraction. The chain was closed. 250,000 tons over 2,000 years. A third of all the mercury that humans have ever extracted. Each ton represents 3 years of someone's life. Shaking hands that wrote nothing down. Now, the finale. Let's return to where we started. Cornwall, the westernmost tip of Britain. The cliffs plunge into the Atlantic, waves crash below, and the mist rolls in horizontally. At the edge of these cliffs stands the Levant Mine Building. It has been here since 1820. The winding house, the engine room. Inside is a steam engine from 1840. It is still operational. To this day, it is the only steam engine of its age in the world that remains in its original location and is functioning. The tunnels extend under the cliffs, further, beneath the bottom of the Atlantic. The horizon stretches beyond the horizon, to the west, deep into the ground, below sea level. The total depth is over 600 meters. The distance of the tunnels from the shore under the ocean is more than a mile. If you walk straight from the machine building along the cliffs towards the sea, then another 1.5 kilometers over the water, there will be shafts beneath you where people once worked. Ask yourself, how was metal extracted from beneath the ocean? Miners would go down, find a vein, cut the rock, and load the carts. The carts were taken to the shaft. The ore was hoisted to the surface. Water was pumped out, and there was plenty of it, as seawater seeped through cracks in the rock. Steam pumps operated continuously. If the pump stopped for a few hours, the lower levels would fill with water. The entire system only remained operational because the steam engine on the surface was never turned off. In the 19th century, no complete maps of these tunnels were made. Miners knew their level, their drift, their location. A general scheme existed roughly. What exactly lies at the extreme, farthest levels beneath the ocean floor, no one knows today. Now, back to the man engine, to the mechanical lift we started with. The shaft was too narrow for a standard lift cage. The engineers came up with the following solution: a vertical wooden beam that moves up and down with an amplitude of about 1.20 meters. Wooden platforms, steps, are attached to the beam every couple of meters. Nearby are stationary landing platforms, fixed to the wall of the shaft, also spaced every 2 meters. The beam moves up. You stand on a step, rising to the next level. When the beam reaches the top, you step onto the stationary platform. You wait. The beam goes down. You step back again. Up again. 24 minutes instead of 2 hours of hiking uphill. Sounds like a significant improvement. If you don't think about the details. Detail 1. Lighting. It was dark in the shaft. The miners held candles. In their hands, because both hands were needed for balance with every step. The candle between their teeth. This is not a metaphor. That's how it was. The flame just centimeters from their faces, while their bodies balanced on a moving platform. Detail 2. Miners at the end of their shift. A person who has worked for several hours in a 30-degree humid environment is physically exhausted. Reactions slow down. Attention wanes. It is at this moment that they must step over precisely and in sync with the movement of the barbell. The number of people who have fallen, there are no complete statistics. This was not reported in the official reports. Detail 3. New workers. It takes time to learn how to work with the man engine. Several weeks of practice are necessary. A new person on the initial descents was deadly dangerous, not so much for themselves, but for those below. A wrong move could send someone crashing onto those who were underneath. Ask yourself, was there an alternative? By 1919, yes. Normal lift cages had existed for several decades. Other mines had utilized them. Levant continued to operate with the man engine because converting the shaft to a cage meant halting production, undertaking extensive mining works to widen the shaft, and investing money that the owners did not have, or that they were unwilling to spend. On October 20th, 1919, around 4 o'clock in the evening, a group of miners was being lifted from the lower levels. The rod was moving. People were jumping. At some point, the wooden lever system, which had been operating at the limit of its wear for many years, collapsed. The platforms fell. The people standing on them fell too. Some managed to grab on. Some did not. 31 people did not return home. Some bodies were found immediately. Some were discovered days later, because the tunnels beneath the ocean are a maze. Some were never found at all. Now, let's focus on one detail that has been overlooked. Shortly before the disaster, the mine inspector visited Levant and noted in his report that the man engine system needed attention, that a number of wooden components showed signs of wear, that an inspection and replacement of certain parts was necessary. The report was written. The report was received. No one closed the mine. No one ordered the man engine to be stopped for repairs, because a halt meant downtime. Downtime meant losses. Losses meant a conversation with shareholders in London. 31 people is not an accident. It is the result of a chain of decisions, each made consciously. Do not spend. Do not stop. Do not change. The wooden beam was cheaper than the plain one, until the day it became the most expensive of all. After that, Levant was closed. And beneath the rocks, beneath your feet if you are standing by the machinery building, there are tunnels. They haven't vanished. They are just empty. Water has likely flooded them, partially or fully. No one has conducted a systematic inspection. What lies on the distant horizons beneath the bottom of the Atlantic is unknown. Official maps are incomplete. There are no unofficial ones. There are shafts that the miners blindly dug, following the vein wherever it led. The vein did not ask, "How far is it from the shore?" It went on, and the people followed it. To what limits? No one checked after 1919. And now add one more fact. The Cornwall mines extended underneath the seabed for considerable distances. In some places, the top layer of rock above the shaft was so thin that it was breached by waves during violent storms. Between the people and the ocean, there was less rock than the walls of an ordinary house. They could hear the storm above their heads. They knew. And yet they descended, because there was no other choice. Levant is not just the last point on our list. It is an accurate depiction of how the entire system operated. Risk is down below. Profit is up above. Accountability is nowhere to be found. Pershibram paid symbolically, a coin instead of an explanation. 319 lives, like an allowable line on a balance sheet. Red Jacket paid financially. Insurance without logic. 8,000 horsepower for a barrel that hadn't extracted ore in the first years of its existence. Monkwearmouth paid with geological risk. 8 years and a fortune spent in a place where coal couldn't exist. Morovelho paid with human bodies. Slaves in 55-degree heat. 2 collapses, a continuation against the economy. Dolkoth paid with unplanned biology, a tropical parasite in Cornish granite, anemia that shouldn't have existed at this latitude. The Tarn Mountains paid with an anomaly that paradoxically became a resource. Endless water transformed into a water supply for an entire industrial region. Levant paid with lives directly. 31 people for a wooden beam that wasn't replaced in time. 7 prices. None of them are recorded in the official balances. But before asking the final question, add one more point to this picture. Karnataka, India. Kolar Goldfields. 1902. The mines here had already reached depths of over 3 kilometers. The pumps at that depth required such a volume of energy that no steam engine was sufficient. British engineers made a decision. A hydroelectric power station was necessary. It was built at the Shivana-Samudra waterfalls, and a transmission line was laid for 140 kilometers through the Indian jungle. Stop. 140 kilometers in 1902 in India. It was the longest power transmission line in the world at that time. To install it through the jungle, intermediate substations had to be built. A system to protect against tropical storms had to be developed, and the challenge of insulating cables in extreme humidity conditions had to be addressed. All of this involved practical problems that had never before been solved over such a distance. The solutions found by Kolar's engineers later formed the basis of standards for long-distance electricity transmission throughout Asia. As a result, the city of Kolar, a provincial mining area in the Indian hinterland, got electricity before most European cities, before neighboring metropolises, before many districts of London. The locals referred to Kolar as Little England. Golf clubs, tennis courts, a library, well-lit streets, telephone connectivity, straight from a mine shaft at a depth of 1.5 kilometers to the company's London office. In 1902, a miner in the Indian jungles could call London faster than residents of many British towns. Ask yourself the question, what was this built for? For gold? Gold in Kolar was extracted even without electricity. The pumps operated on steam engines. Electrification was not a necessity for mining. It was a necessity for mining at that specific depth that someone had already decided to reach. Depth did not follow technology. Technology was built for a predetermined depth. Someone already knew how deeply they needed to go. Before they built the hydroelectric power station, before they laid the cable, before they cut the last kilometer into the granite of the Deccan. Who decided to dig here, to this exact depth, with these specific costs, and at this very moment? Not the market. The market does not build insurance shafts with pumps for megacities. Not science. Science has prohibited coal mining where it was found. Not simple commercial interests. Commercial interests have long demanded the closure of Morovello. Look at the timeline of all 7 objects as a single chronological line. Moncurement, 1826. Britain transitions its fleet to coal. Morovello, 1834. British gold penetrates deep into Brazilian soil. Tarnowski Mountains. From 1784, Prussia launches the first steam engine on the continent to avoid sinking in its own waters. Dolkoth. Early 19th century. Tests of high-pressure steam that will be used in locomotives 20 years later. Pribram, 1875, the first kilometer and an international school of methods. Almadin, continuously, from the 3rd century BC to 1863, the mercury monopoly controlled the silver economy of 2 continents. Red Jacket, 1889, right at the moment America begins mass electrification. Levant, operated until 1919, until the last day the wooden pole held. And the Satro Tunnel in Nevada, 6 kilometers through rock, constructed from 1869 to 1878. One man against the Comstock banking cartel. Engineer Adolphe Satro carved out a tunnel that pumped 4 million gallons of hot water from silver mines every day, effectively dismantling the monopoly of banks controlling access to the ore. When the tunnel was operational, Satro immediately sold his share and moved to San Francisco. He became the city's mayor. The tunnel continued to pump water for decades after his death. This is not a random scattering of objects. It is a sequence. Each subsequent step into depth matched a new technological threshold on the surface. Coal for the fleet. Gold for the currency standard. Steam for transportation. Copper for electricity. Physiological data for future industries that did not yet exist. And now, the last thing I want to add to this picture. In Germany, in the Harz Mountains, the Grube Samson mine had been operational since 1521. Silver, 810 meters deep. But it is not the depth that makes it special. What makes it special is that the entire system operated without steam and without electricity. Only water. Mountain engineers built a network of 60 reservoirs, hundreds of kilometers of channels, and a system of wooden mechanical rods that transmitted the energy of water over distances of several kilometers, driving pumps at a depth of 800 meters. This was called Stangenkunst, a system of rods. Wooden beams moved back and forth, just like pistons, transmitting force along their entire length, horizontally across mountains, for several kilometers. Without a single electrical connection, without a single piece of coal. This continued to work until 1922, almost 4 centuries. The wooden mechanisms of the 18th century survived the Industrial Revolution, both world wars, and made it to the radio era. Ask any engineer, is it possible? They will say, theoretically, yes. Practically, it requires constant maintenance, continual replacement of parts, and ongoing monitoring. This means that for 4 centuries, generations of engineers have passed on a precise understanding of this system to one another. Any break in the chain of knowledge, and the system dies. It has survived because someone every decade understood it from the inside well enough to keep it going. This is the true value that the mines of the 19th century produced. Not silver and not gold. Not coal and not copper. An unbroken chain of understanding of how the world works underground, and what one needs to know to descend there and return. Look at what remains. A steam engine from 1840 in the Levant still operates today. The wooden poles of Grube Samson have stood for nearly 4 centuries. The Tarnowski Mountains tunnels still supply water to regional water supply systems. The depth of Pribram is still considered a world record for silver mines. The drainage adits, hand-carved 200 years ago, have not collapsed. They simply exist there. Beneath the mountains, beneath the cities, beneath the ocean. Made without computers, without modern alloys, without GPS navigation in mine shafts. We build today for 100 years and call it eternal. They built in a way that it outlived us, even before we were born. Someone has been monitoring this chain. Someone was making decisions with a planning horizon longer than that of the shareholders of the mining company. Someone was building for centuries, not just for recoupment periods or the next quarter. This is why the machines are still there. This is why the tunnels are still there. There is no answer, but now the question has been asked correctly.